In this video, we will be learning about writing chemical formulas for elements and compounds. Primarily, we're going to be writing empirical formulas and molecular formulas and learning how to interpret structural formulas. So we do have to connect our chemical symbolism to molecular representations and what it means, because where we write our numbers does communicate to other people what you're talking about. So if you just write H, it's referring to single atoms. You can have, if you just write H, it's just referring to one hydrogen atom. If you put a 2 in front, it means that you have two separate H atoms. They are not bonded together. If you write a 2 as a subscript on the right-hand side, then it does mean that those two H atoms are bonded together. So you can see here that they are connected together. They are touching. And so if you write 2H2, then that is two different H2 molecules. So two separate H2 molecules. So the number up in front means that there's two of them, and a subscript 2 means that it's connected together. So numbers up in front, not connected together. Subscript is connected together. So when we write chemical formulas, we can either write empirical formulas or molecular formulas. Empirical formulas indicate the lowest whole number ratio of elements. The empirical formula is not completely useful for molecular compounds because we do have different compounds, completely different compounds that have the same empirical formula. So this chemical compound is benzene, which has a molecular formula of C6H6. But the lowest whole number ratio would be 6 and 6. Well, both are divisible by 6, and so the lowest whole number ratio is 1 of each. Ethine has 2 carbons and 2 hydrogens. 2 and 2 are both divisible by 2, and so the lowest whole number ratio is just 1 of each. And so for these two different molecular compounds, the empirical formula isn't exactly informative, but that is the definition of empirical formula, is the lowest whole number ratio. For ionic compounds are always reported as the lowest whole number ratio that represents the cations and anions that make up the compound. And so for ionic compounds, the formula for an ionic compound is typically the empirical formula. Molecular formulas tell you exactly how many of each different atom are in the molecule, how many are bonded together in a molecule. Remember, molecules are discrete units, not continuous structures. And so molecular formulas are only for molecular compounds because they tell you exactly how many of each thing there are. But a molecular formula doesn't tell you how the atoms are connected together. And so there are many different substances, many different compounds that have the same molecular formula, but different structures. And so an example of two molecules that have the same chemical formula but different structures are 2-propanol and 1-propanol. They both have a molecular formula of C3H8O, meaning that they have 3 carbons, 1, 2, 3, and 8 hydrogens, which are represented by white, 1, 2, 3, 4, 5, 6, 7, 8, and oxygen is represented as red. And so there's 1 oxygen. You can see that the subscript 1 is implied for the oxygen. go ahead and pause the video and try to work out the empirical formulas for each of the chemical formulas given. Unpause the video when you are ready to double check your work. Okay, so we'll go over this. Both of these subscripts are divisible by 2, and when you do that, you end up with HO, or HO. 3 and 6 are both divisible by 3, and so you end up with NO2. Mg, you gotta remember, it has a subscript of 1, and so the lowest common multiple of 1 and 2 is 1, and so MgI2 is already in its empirical formula. For this next one, we have our subscripts are 6, 12, and 6. All of those are divisible by 6, and so our ratio is 2, no, that's for the hydrogen. 1 carbon, 2 hydrogen to 1 oxygen. And now for this next one, this is an example of an ionic compound where the chemical formula is not the empirical formula. So for this ionic compound, this is a oxalate ion. We'll get into our polyatomic ions in a later video, but each oxalate has 2 carbons and 4 oxygens. And so we have to keep that as C2O4 if we're going to represent the ionic compound, but this tells us we have to write the empirical formula of it. And so all of these are divisible by 2, and so the empirical formula is NaCO2. Okay. So our empirical formulas and our molecular formulas don't necessarily tell us what compound we have, but we will be working with them quite a bit. As you progress in chemistry, you will see lots of structural formulas or structural views of different molecules, and that's to convey how the atoms are connected together. So a structural formula will help tell you which compound you have, because it will tell you how those atoms are connected together. And so we have molecular formulas, which don't really tell you much. This structural formula tells us the chemical symbols for the different elements, and then uses lines to represent bonds between those different elements. But this doesn't really give you a view of what the molecule really looks like, and so there's other models where they try to use either, this is known as a ball and stick model, where the atoms are represented by colored balls. And then this is a space filling, which is the closest we get to an actual molecular view, because the atoms are smushed together in space. This compound is benzene, so I also have a macroscopic view of benzene. So this is a sample of benzene. These molecules inside, if we were able to zoom in, would look like this space filling model. Except for they necessarily wouldn't be colored like that. The color coding here is known as CPK coloring. In ball and stick models and space filling models, we color code the different elements. And so the colors that you're expected to recognize are hydrogen being recognized, hydrogen is white, carbon is black, blue is nitrogen, oxygen is red, and if you see any green balls, it's either fluorine or chlorine. And so this structure down here is an ionic compound of NaCl. This is glucose, which is C6H12O6. And so you can see there's 1, 2, 3, 4, 5, 6 red balls, and so that's glucose. And this is caffeine, one of my favorite molecules. So the word for different compounds that have the same molecular formula is isomers. Isomers have the same molecular formula. There are different types of isomers, and so if you go on to take organic chemistry, you will learn all about different types of isomers. Structural isomers have a different connectivity of atoms, and so you can see here the acetic acid, which is also vinegar. So if you're going to go in your kitchen, vinegar is acetic acid, C2H4O2, and methylformate is not edible, don't eat that, but the connectivity is different. So these two carbons are connected directly together, and in this one, the oxygen is a bridge between the two. So different structures, different connectivities, and so these are structural isomers. These two different molecules, glucose and mannose, have the same connectivity. So if we look at the molecule, we have CHO on top, and then C bonded to one OH and H, and then each carbon down is bonded to one OH and H, and then the bottom one is CH2OH. The difference is here. And so this part of the molecule is actually a mirror image of the other substance. And so in 3D space, this is going to have a different compound. In 3D space, this is going to be different right here. And so since they are different, they do have different chemical properties, and so they are different substances. And so these are spatial isomers, also known as stereoisomers. I think your book calls them spatial isomers, meaning they are different in space.